Okay, on three we say, hi, Claire. 1, 2, 3.
Hi, Klara.
Wow. Okay. That was amazing. All right. So there's problem 28. Look at that. Technology is amazing. Problem is, the icon strip doesn't work, so I gotta find it on here. Everything takes a fortnight. Yay! All right. All right. So number 22 worked out okay, right? Not too terrible. Number 28 has to do with this problem right here, the two rings and the electric field and all that goodness. So what we need to do in this problem is basically remember that the E field, all right, here we go, draw mode. Everything has to blink 6 times. That the E field of a ring, when you are above the center, above the plane of the ring, the equation is K Q Z, where Z is your distance above the center of the ring, over Z squared plus R squared to the 3/2 on the bottom, and I think that's the whole thing. So for this problem, if you're right there at P, that equation tells you the E field due to the outer ring and the inner ring. Now the inner ring is a positive charge Q. The outer ring is what sign? Negative, because its E field's got to cancel the E field of the inner. So this guy is negative. And apparently it's some multiple of the inner. Now, last hour somebody said, I never would have thought of saying N times Q for the outer. And I said, that doesn't matter. You still would have been fine. If you called the inner ring inner, Q inner, and the outer one Q outer, and you found the ratio of the two, you'd be fine. I just called the inner guy Q and the outer guy N times Q because I love to cancel stuff out. We got to wah out the Q's that way. It's a weird little trick, but it works. So what we'll do is we'll say, all right, E inner minus E outer equals 0. Or E in equals negative E out.
Yeah, this would be plus, right?
On the top.
Adding up the inner
First
now.
one.
Oh, I beg your pardon. You're absolutely right. Yeah, adding up the two E fields should give us 0. Therefore, one is the negative of the other. Okay, so what we're going to do then is use that equation at the top and say, all right, for the inner one, we've got K, Q. Now Z is not Z. Z is 2R, right? That goes all the way to the center of the ring. So don't write Z, write 2R. On the bottom, we've got 2R. Now be careful. This is where people mess up. They write 2R squared. It's not 2R squared. It's 2R squared. The whole thing's squared. So it's 2R quantity squared. And then the R for the inner guy is R. Okay, and then the outer guy, we're going to have K, N times Q, or Q outer. We're still 2R above it, so Z becomes 2R. On the bottom, Z is still 2R, but it's 2R quantity squared. And R, the radius of the big guy, is 3R. So I've got 3R squared. And the whole thing is raised to the 3/2 power. And then you just go for it. Okay? The K's cancel out, the Q's cancel out, the two R's on top cancel out, and down at the bottom, 2r squared is 4r squared. 4r squared plus r squared is 5r squared. So that what's in that parentheses becomes 5r squared. Down here, I've got 2r squared, which again is 4r squared, plus 9r squared, 13r squared. So when you're done canceling stuff out, you have, I'll do it over here in the corner. Sorry, Klara. 1 over 5r squared equals negative 1 over 13r squared, and these are both raised to the 3/2 power. And then you realize right away that the r squareds are now going to go away. Oh, I'm sorry. I forgot my n on top here. We're trying to find n, the multiple. So when we're done, we've got 13 to the 3/2 over 5 to the 3/2 negative equals n. And so if you punch that out, take 13/5 and raise it to the 3/2 power, you get like negative 4.19. So n equals negative 4.19. So the outer ring is just slightly more than 4 times the charge of the inner ring, and it's negative. Okay, so that's the kind of problem you can kind of count on for these. I'm not going to ask you on the test to derive the equation for the ring. Could that be on the AP test? It's possible. It's certainly not probable that they would say, oh, look, here's a ring of charge derived from first principles, the E field at some distance above the plane of the ring. They could say that. That's kind of why I went through the derivation, partly to give you the concepts of how to do it, and partly to make you really familiar with it. All right. Any questions on the assignment? You all good? Those of you who got it right, you're kind of bored for the last few minutes, but we got it recorded. All right. Next thing. I was going to give you an assignment last night that included a few more problems, but thought better of it because there's a couple things here. As we take a look at some of these, I had you do 22. I threw in 28. I'm going to throw in 25 and 30. But before doing number 25, let's take a look at it. So what I need to do is create a blank screen. There we go. Okay, if you look at number 25 in the textbook, if I had given this to you last night, this is kind of a doozy. It says 2 curved plastic rods, one of charge plus Q and the other one charge negative Q, form a circle of radius R, 8.5 centimeters in the XY plane. The x-axis passes through both of the connecting points, and the charge is distributed uniformly on both rods. If Q is 15 picocoulombs, what are the magnitude and direction relative to the positive direction of the x-axis of the electric field E produced at P and at the P, the center of the circle? So, here's the deal. We've got this ring. Love it. The delay makes it almost impossible to draw a circle. Okay, there we go. That's a lot better. And I've got an x-axis passing through it. Y-axis, it's not the best in the world, but okay. So ring, and on top we have positive Q. So this is positive charge, positive charge, positive charge. On the bottom, we have an equal negative charge. So, negative Q, bottom half, positive Q, top half. You okay? Radius of the circle, 8.50 centimeters. Q, 15 picocoulombs. Okay. Now, looking at my handy dandy chart here, a pico is 10 to the minus 12. For some reason, that was not on the top of my head. 10 to the negative 9, nano. 10 to the negative 12, pico. Crazy. Okay, my students. Suppose we look at a point right at the center of the circle, assuming that's the center of the circle. What's the electric field direction due to just the positive half of the ring? What's the positive half of the ring going to do? Push it straight down, right? Because if we look at just a piece of the ring here, like right here, look at just the charge there, it's creating an E field directly away from it. And if I add up all the effects of all those pieces.
Oh, can I borrow Joel for a second? Or
If he's willing,
he's
going to miss this. If I add up all the pieces here, I'm going to end up with an E field pointing straight down. What about the bottom guy? The bottom half is negative. So if I choose any piece, the electric field is going to be toward that piece. What's going to be the direction of the net field due to the bottom half? Straight down. Okay, so the field due to the top half is going to be straight down. The field due to the bottom half is going to be straight down. What do you think about the magnitudes of the field created by the top half compared to the field created by the bottom half? The same. Okay, it's the same charge, the same radius. It's just one is positive, one's negative. They're both creating a downward field. So when you do this problem, and you will do this problem, I'm not going to do it. My suggestion is just do the top half, and when you get the answer, double it. So don't do the whole problem. Do half the problem, and then say, well, the other half is going to be the same. Are you okay with that? Is that logical? Okay. So we're going to just do this half of the problem. And it's all positive. These are all little positive charges. And total charge is Q. And we're going to find the E field just due to that and double it. Makes our lives way simple. Okay. I don't have an equation for this. I do not know what the answer is. The equation we have for a ring is for a full ring. And if we set z equal to 0, we're going to get 0 because the ring will cancel out if you're at the plane of the ring at the center of it. So we don't have an equation for this. So this problem is actually asking you to derive the equation for this and then use it to get the answer. So what are you going to do? What you going to do? What you going to do when they come for you? Oops. Keep going that way. Okay, what did we do yesterday? when we were dealing with the ring and we were in the plane, we were above the plane of the ring. Take a little piece of it, say, oh, there's a chunk. And it has length ds, and it has charge dq. And we'll add up all the effects of all the little chunks. Okay? That piece of the pi here is going to create an E field in that direction. A little piece of the total field. And let's call this angle theta. And this angle theta. And when you break this guy down into components, I've got dE sine theta, dE cosine theta. And when we add up the effects of all those pieces, what's going to happen to the horizontal component? It goes away. So we, again, just like before, we only need to add up one of the components. We only have to add up all the dE cosines of theta. Okay? So, E equals the sum of all the dE cosines of theta. Okay, what's dE? What's the electric field due to one little piece of charge? Do we have an app for that? I love it. Okay, so our app is KQ over R squared, so we'll just say it's K dQ over R squared. So let's use their capital R and do it. Beautiful. Now, this is why I wanted to do this with you, because you wouldn't have, you might have, but I don't think you would have thought of this. We're actually going to integrate this thing from theta equals pi over 2 to theta, oops, I did it backwards, didn't I? Theta equals pi over 2 to negative pi over 2. Sorry, Klara. So look at my diagram. If this is the angle, that means 0 is straight up and down. So we're going to integrate from 90 degrees, from negative 90 degrees to positive 90 degrees. There we go. So our beginning spot is going to be negative 90 degrees. We'll go all the way around to, which means that we can't leave that as dq. We need a d theta there. I was talking to Ms. Stoughton. This is one problem that doesn't show up in calculus, where the variable of your limits is different from your variable of integration, and you got to fix it. She asked me yesterday during lunch, how could that ever happen? I'd say, well, here are a couple of examples. It always happens in physics. You set up the integral and you say, darn, I can't integrate that. The limit variable is different than the variable in the integration. So you got to fix it. So we need to rewrite the dq so it doesn't say dq, it says d theta. So how the heck are we going to do that? Okay, there we go. Just need a little space. Okay, here's what we're going to do. We're going to say, remember this lambda thing. Lambda is the total charge over the total distance. So in this case, we could say that it is dq over ds. Okay, which means that dq is equal to q ds over s. Now s is the length of the entire thing, because this is total q, this is total length. What's the length of this guy? I heard Jake say it, or somebody in this region said it. Pi r, because the circumference is 2 pi r, and we've got half a circumference. Some days, Jake, you are just awesome. It was almost immediate. I said, what is it? And he said, pi r. He's got a fast brain. Okay, that gets us partway there. We've got dq written as ds, but we don't want ds, we want d theta. Now, d theta, this is kind of weird, folks. Hang on to your hats. D theta is this little bit of angle here that is created by our ds. So that little guy is d theta. So remember how radian measure works. Radian measure works, it says radians is arc length divided by r. Our arc length in this case is ds. So I kind of messed that up. Sorry, Klara. But by the definition of radian then, d theta, the tiny little angle, is equal to the arc length, ds, divided by r. So instead of saying ds, we're going to say r times d theta. And I'll use their big R. So back here, we're going to say dq is q times r d theta. Wah! Lose the r. So now we can replace dq with q d theta over pi. And then we're ready to integrate. When you finish up the integral, remember you can pull out the constants. So what are our constants? Is k a constant? Obviously. Is q a constant? The total charge. Total charge is a constant. Is pi a constant? Obviously. Is r a constant? The radius of our half circle. So we can pull everything out but the cosine of theta and d theta. What's the integral of the cosine of theta? Sine of theta. Okay. And then you can evaluate it between those two angles. So I didn't want to just, I had this on my assignment list, and then I said to myself, you know, if I just send this home, they're going to be kind of upset with me. And obviously, correctly so, because we just did one problem, we did one derivation yesterday with that silly ring, and then for you to extrapolate how to deal with a half a ring when you're at the plane of the ring is a little bit of a leap there, a big leap. So, how are you doing? I know this, it's not going to be this hard all the way through, so don't get the impression like, you know, oh no, I shouldn't have taken the second semester, I'm going to jump off the auditorium. This is just particularly hard right now. Later on, we'll do stuff and you'll go, oh man, that's nice. Next chapter is Gauss's law. As soon as you get over some of the weirdness of Gauss's law, you're going to say, oh my gosh, where have you been all my life, Gauss? You make the problem so much easier. So I don't want you to get the impression like you've just dug yourself into something really terrible for the next 90 days. But this is particularly difficult, especially since many of you are just starting integration in calculus. If you had it last year, it might be a little fuzzy in your brain, but at least you've been through it. If you're just starting integration right now, you're looking at this going, holy moly's, this is a little bit advanced. In a perfect world, I'd be doing this, like in April, after you've done a zillion integrals and you're ready for something like this, an application like this. So, if you're a little shell-shocked, please don't be worried. We will do this. Okay, so your assignment will be 25 and 30. Let's do a couple other things before we hit the end of the hour. The book does a nice derivation for a disk. It's also on the AP syllabus, so could it be there? I don't know. I'm not going to do the derivation. You've had enough of that for one day, and I don't really see the purpose at this point doing it. It does involve integration with substitution, which I'm told by Ms. Stoughton you just did. The integration with u. So you need that for this derivation, even though I'm not going to do it. So if you're interested, I could give you a copy of the derivation, or we could do it, after school or sometime when we have a moment. But the thing is, if you have a disk, and the disk has a surface charge on it, it's all covered with charge, and you are some distance above the center of the disk. Okay? Looks familiar. It's the same problem as the ring, except now it's the whole disk, not just a ring. And the charge density on the ring is a surface charge density. Okay? Better way, instead of saying area density, better way of saying it is charge per unit area, right? So what's the electric field at P? What you actually do is, I'm not going to do this, but what you actually do is you turn it into a zillion rings. You say, okay, the electric field due to one ring, that ring has a charge dq, it has a thickness dr, it has a radius of some random r, and the whole thing has a radius of capital R. And you would work your way through it by integrating the effect of all these rings. You just add them all up. And it's really cool. It's a cool derivation. Because we already have the equation for a ring, so we say, why not use it? We'll use it infinite number of times, and we'll come up with the answer. And so it's kind of nifty. The answer is, and obviously I don't have it memorized, so I wouldn't expect you to either. Is that puppy right there? Now, clearly there was a k involved here, and by the epsilon naught, you know that they must have, instead of saying k, they said 1 over 4 pi epsilon naught. So remember, k, 1 over 4 pi epsilon naught, and epsilon naught is that crazy permittivity constant that we were talking about yesterday. All right, so there's some problems in the assignment where they're going to assume you know this equation. Z is still your distance above the center of the disk. R is the radius of the disk. There was a question. Oh, no, I thought I heard somebody. Very good. So that takes care of that. Nope, I'm going to add a little bit to your assignment there. So hang on. Oh, one thing. What happens to our answer here if this disk is really, really big? What if we let R approach infinity? People used to believe in flat Earth. The Earth is a flat disk. So if we were on a flat disk that big, what would happen to our equation? If we're talking about, R is like 6 million meters. If this gets real big, if R gets real big, what happens to this term? It goes to 0. And E gets really close to sigma over 2 epsilon naught. That's infinite sheet of charge. So if you had this huge sheet of charge and it was uniformly charged and you were hanging above it, this equation tells you the E field there. So that sheet of charge is really, really, really big. So that's like the size of Michigan, and you're a few feet above it. What's not in this equation that you might think should be? How far are you away from the sheet? An inch? 2 inches? 2 miles? Where is the distance above the sheet? It's not there. No matter how high you are above the sheet, E is the same. Why do you think that? Why do you think that's true? Think about the electric field lines coming off the sheet. Are they diverging? Are they coming together? Or you think they're parallel? Yeah. They'd have to be parallel. There's nowhere for them to go. They can't cross in the... Goodness sakes, my marker is dying here. And they can't cross because the charge next to them is sending out E field lines, and this darn thing is infinite. So it doesn't matter. You could be an inch away or a light year away, and E is the same. But that would be for an infinite sheet. I haven't never noticed an infinite sheet lying around somewhere, so... but it is kind of a cool result. What happens if Z gets really, really tiny? If Z gets really, really small, if Z starts approaching 0, you get the same result. So it's kind of like scaling down. If you become Ant-Man and you get like a millimeter away, the disk starts looking like an infinite sheet. So what's kind of weird about this equation is if R gets really, really big, you get this result. If Z gets really, really small, okay, you go down to Ant-Man size and you say, hey, I'm, a 15th of a millimeter above this thing, it starts looking like an infinite sheet again. So it's kind of funny. It's a scaling thing. Alrighty. All right, how am I doing on time? Yep. Okay. We're doing well. Okay, let me just make sure. We are there. All right, so 2230, number 36 is one of those infinite sheet things. Okay, last thing we got to do before we hit the end of this unit is deal with this situation. Okay, see if I can make this work. All right, a tiny drop of oil has a mass of 5 times 10 to the minus 9 kilograms and a charge of -2 picocoulombs, and it enters the region between two oppositely charged parallel plates. The oil drop begins near the negative side with a velocity of 30 meters per second, parallel to the plates as shown. The electric field between the plates is uniform, and neglect the effects of fringing. And has a magnitude of 3.1 times 10 to the 6 newtons per coulomb. Determine how much vertical deflection is experienced by the oil drop when it has reached the opposite end of the plates, 0.25 meters away. So this guy, this little negatively charged thing, has some velocity. It's whipping through. And it's very, very, very light. I mean, the mass is extremely small. So for our calculations, we're actually going to neglect its weight because much, much, much more powerful is the electric force on this thing. If the electric force didn't exist, this thing would basically, with a little bit of bending, go straight through. But because of the electric force up toward the positive plate, he's actually going to follow a path which will take him like, whoa. Oh, that's not bad at all. Look at that. So his original path, his deflected path, and they want to know, okay, what is that? How far will it be deflected? Wasn't it just the anniversary of the invention of the television?
Yeah.
This is it right here. You have plates that can deflect a beam of electrons. And if you can deflect a beam of, if you can put a beam of electrons anywhere you want, you can actually use the electrons to cause phosphors on a screen to light up. And then if you scan that beam really fast, turning it on and off as necessary, you can make a picture. So there's some technical applications to this, being able to take a beam of electrons and put it where you want. We don't use it as often anymore because now we have flat screen TVs, but it still has technical applications. Okay. So let's see. We have the size of the E field. We have the mass of the drop. We have the charge on the drop, which is negative 2.0 times 10 to the minus 12 coulombs. Okay. As it goes through, what's the direction of the force on the drop? You got it. So here's our electric force due to the electric field. I better say F sub E, sorry. F sub E going up. So if we take a look at its motion, what kind of motion will it have on the x-axis? Constant velocity. And what kind of motion will it have on the y-axis? Constant acceleration. Have we done this before? Does this ring a bell? Okay, before it was, you throw a rock off a cliff. And what would it do on the x-axis? Constant velocity. And what would it do on the y-axis? Constant acceleration. We just flipped it, right? I did that on purpose. So it's projectile motion upside down. We're going to do the same thing. So, I don't have any room to write, Klara. So what we're going to do, though, is we're going to say, all right, x and y. Split the problem up. On the x-axis, we're going to say v naught delta t. Tells us how far it goes on the x-axis. On the y-axis, we have no initial velocity, so we've got delta y equals, let's see, 1/2 a delta t squared. Okay, are you in agreement? You remember this stuff? So on the x-axis, we have initial velocity, but we have no acceleration. So on the Dragon equation, I'm only going to use the front half of it for the x-axis. For the y-axis, we have no initial velocity, but we do have acceleration. So I'm going to use the back half of the Dragon equation. And in those two equations, what are we trying to find?
Delta Y.
Exactly. So we're looking for delta y. When you look at the x equation, what do we know and what could we find? Do we know delta x? 1/4 of a meter. Do we know the initial velocity? 30 meters per second. So we can figure out exactly how long it spends in between the plates. So we could say, all right, delta t is delta x over v naught. So 0.25 meters divided by 30 meters per second. Time between the plates, 0.00833 seconds. Okay? Really short amount of time. Exactly. Delta y, I'd like to know delta y. I got delta t. How am I going to get a? What's the how can I find the acceleration of this little guy? F equals ma. So I'll do it over here. Remember, electric field is force divided by charge. So the force is the electric field times the charge. I know what the electric field is because they told us. I know what the charge is because it's an electron. So I'm going to say EQ equals MA, or A equals EQ over M. Okay? Oh, I'm sorry. It's not the charge on an electron. I take that back. I'm thinking of a different problem. It's an oil drop with a charge of -2 microcoulomb, or picocoulomb. So -2 times 10 to the minus 12 coulombs. So I beg your pardon. We're going to put that in for Q. We know E is 3.1 times 10 to the 6. We know the mass is 5 times 10 to the minus 9 kilograms. So we can come up with the acceleration, and we can come up with delta y. So over here on the end, finding delta y, we're going to say 1/2 the acceleration, EQ over M, times delta t squared, which we just calculated over on the x side. So that solves the problem. So the last section in chapter 22 is called Charge in an External Field. So a charge creates its own field, but that's in that section, that's not what they're talking about. They're talking about what happens to a charge when you set it in an external field, a field created by something else. And so this is a good example. Send a charge between two plates, charged object between two plates. Its trajectory is easily calculatable using math that we already came up with. Now, if it bothers you that we didn't worry about gravity, you could try it out. You could do an mg down and see how that affects the acceleration. And I have a feeling your answer is not going to change too much. Okay, so I would say that we've kind of reached the end of the unit. So the assignment is going to be, please do 25, 30, 36, And I'd like you to do a couple of these point charges floating in an E field ones. So that's 43 and 48. Okay, and I have good news and I have bad news. The good news is you've got till Monday to do this, because I will not be here tomorrow. The bad news is I won't be here tomorrow. And I will also give you the review to work on as well. So don't put this off until Sunday night, because you will have other things to do. But you'll have class time tomorrow, obviously, because the chances that the sub knows AP Physics is probably pretty small. It has happened, though. I've had physics teachers who are looking for jobs come and sub for me, and they've helped students out in the past, sort of. It's kind of dicey sometimes. But chances are the sub will just hand out the review and say, okay, guys, you know what you're doing. So, sorry, I won't be here tomorrow. I will see to it, I will attempt to get all my problem solutions up so you can check these things out. I believe they're on Moodle, I just have to unhide them. If that's the case, it's an easy fix. If not, I'll have to do a little bit more work, and it depends on how long Elaine stays after school tonight. Just kidding, I'll get it done. All right, so I will see you on Monday. So that's all I have. I better turn this video off before Claire has to watch a 6-hour video. It's already 46 minutes.